All right, so let's start talking today about Fourier transform of periodic signals. We will take a look at a few more properties of Fourier transform. We'll talk about duality property, time multiplication property, frequency shifting, and some very useful symmetry properties of Fourier transform. And then we will get into an application of Fourier transform, which is communication systems. So communication systems discussion will be very generic and applicable to essentially communication between 2 points, and we are going to specifically focus on amplitude modulation. Okay, so let's talk about Fourier transform of periodic signals first. So if you have a periodic signal, say x of t, and it is periodic, so it has to have some period cap t that exists such that x of t equals x of t plus cap t, right? That's the definition of periodicity. And since x of t is periodic, we can express that as an exponential Fourier series, as a summation like this, where x of t is a sum of Fourier series coefficients a sub k that are multiplied by the orthogonal set of functions, which are exponential Fourier series in this case, e to the jk omega naught t, where omega naught t, where omega naught is simply 2 pi divided by cap t, where cap t is your time period of the periodic signal. So we know this from before. Now, let's try to use the frequency shift property that we learned in the previous lecture on this. Over here, the claim is that in time domain, if the signal is e to the jk omega naught t, then in the frequency domain, its Fourier transform is 2 pi and an impulse at k omega naught. Well, where are we getting this from? We are getting this from by applying the frequency shift property. So let me just capture that over here. So what is the Fourier transform of a constant, say 1? Well, the Fourier transform of a constant is simply going to be an impulse, but scaled at 2 pi. Now, when you have a frequency shift, what do you have? You multiply in time domain by, say, let's use k omega naught. K omega naught t, then that is a frequency shift of k omega naught. So we have essentially captured that in here. Now ak, these coefficients ak, are simply constants because they only depend on k. So we can use the linearity property such that we are trying to take this time domain signal towards x of t to represent that as a summation. So how can we do that? Well, first I need to multiply that by ak. ak is a constant with respect to, it's only dependent on k. So I can multiply the left-hand side, in this case the time domain, with a sub k. And if I want to use linearity, I also multiply the frequency domain by a sub k. So that could mean I multiply that with a sub 1, a sub 1, a sub 2, a sub 2, a sub minus 1, a sub minus 1, whatever that is. I'm just trying to multiply the time domain as well as the frequency domain with a sub k. Once I do that, because I'm still able to use linearity, additivity is a part of linearity. So if I can add up all the k's, so if I apply a summation on the time domain signal with k going from -infinity to infinity, that would also mean that in frequency domain, I apply the same summation where k goes from -infinity to infinity. In other words, what I have in my time domain is that periodic signal after I use linearity. The Fourier transform of that is simply going to be all of these pieces here with an addition of the summation over here. And that summation only depends on k, so I can pull out that 2 pi factor outside of that summation. So 2 pi multiplied, so 2 pi summation k equals negative infinity to infinity. A sub k, those are the Fourier series coefficients of x of t multiplied with delta functions, impulses present at k omega naught. So using this particular result, we can say that if x of t, if the time domain signal happens to be a periodic signal, then its Fourier transform is made up of delta functions or impulses. So impulses in the frequency domain, you have time as periodic. Let us do a few examples here. One is the Fourier transform of the periodic pulse train. So what is going to be the Fourier transform of a pulse train which is on between negative t1 and t1, and it has a time period t. t1 is less than t, so that we have a square pulse, otherwise it will be a constant. For this, the first thing I would need is to refer to the Fourier series coefficients of the pulse train, x of t. What is that? Let us try to write that reference result here. I have omega naught as 2 pi divided by t, and a sub k, the Fourier series coefficients of a pulse train, are 2t1 divided by t sinc k omega naught t1. This is for all k. Omega naught is 2 pi divided by t. So once I know the Fourier series coefficients of this pulse train, then I can use the earlier result of Fourier transform of a periodic pulse train and along with this Fourier series coefficients. So I can say x of t, which is my periodic pulse train, the Fourier transform of that is going to be 2 pi, there is a summation, then there is a k equals negative infinity to infinity, we have ak, and then we have those delta functions at k omega naught. Then I simply substitute my ak. When I substitute the ak result, because this is a known quantity, I've looked at it before, what do I get? Well, let me define this as x of omega. Then what do I get? X of omega, the Fourier transform of x of t is going to equal 2 pi, there's a summation, k equals negative infinity to infinity, a sub k gets substituted, sinc k omega naught t1, where omega naught is 2 pi divided by t, and then I have the delta functions. Rearrange, you can get 4 pi t1 divided by t followed by a summation with respect to k. I'm left with sinc and impulse. Sinc k omega naught t1 and multiplied by impulses, delta functions present at 1 omega naught, 2 omega naught, 3 omega naught, negative 1 omega naught, negative 2 omega naught, and so on. So that's the result over here that I'm interested in. So let me box this up and then we'll try to analyze this result. So they are going to be let me underline these things here. Delta of omega minus omega naught. That means that in the Fourier transform of x of t, I am going to have delta functions or impulses present at 1 omega naught, 2 omega naught, 3 omega naught, and so on, and also at 0 omega naught, negative 1 omega naught, negative 2 omega naught, and so on. And I know earlier when I did this for a square wave, I know that all the even harmonics went to 0 from an and you can see this by substituting k as 2, 4, 6, and so on in this result, and you will see that it evaluates to 0 at those frequencies. So that's one. The next piece is, what does this particular thing mean? That means that my Fourier transform is going to have a sink-shaped envelope, but because I'm only evaluating that sink function at k omega naught times t1, it is going to be the impulses, the delta functions being weighted with that sink being evaluated at k omega naught t1. Then there is a summation. So all those pieces are getting added up. And additionally, you have this 4 pi t1 divided by t value, which is what? That is essentially, let me underline that in red here. And what is that? That is essentially the DC value. K equals 0. How do I know that? Because when k equals 0, sink 0 becomes a 1. Delta is present over there. The impulse is present, delta of omega. So all you get in terms of the weight for that impulse at omega omega equals 0 is going to be 4 pi t1 divided by t. So you have that particular scaling for the DC value. You have a sink-shaped envelope and the impulses that are present at integer multiples of omega naught. So combining all of this, we can sketch the Fourier transform of x of t like that. The impulse that was present at omega equals 0, the scale or the weight of that impulse was 4 pi t1 divided by t. We saw that earlier. The overall Fourier transform had a sinked shape envelope. We saw that earlier. And we also saw that those Fourier series coefficients were going to 0 for even harmonics, and they were non-zero for only odd harmonics. So delta functions being scaled by a sink function, that's your Fourier transform of the pulse string. All right. Next, we have a special case. The special case is the impulse train. So our periodic signal that we are considering here, x of t, is a impulse train, a train of impulses, right? It's a periodic signal with a period of cap t, and the weight of each impulse at 0, plus and minus t, plus and minus 2t, and so on is 1. We know from earlier that the Fourier series coefficients of an impulse train are simply Sk equals 1 over t, and this is for all k, right? X of t can be written as a summation of the Fourier series coefficients multiplied by those exponential orthogonal set of functions e to the jk omega naught t. Ak gets substituted by 1 over t. We have this. Then we know that if we want to find out the Fourier transform of a periodic signal, all we have to do is use this result. 2 pi summation over all k, a sub k is what gets substituted, 1 over t here, and then you have those delta functions at integer multiples of omega naught, where omega naught again is 2 pi divided by t. 1 over t is independent of k, so it can come outside of the summation. All you have is a summation for over k impulse at integer multiples of omega naught. So you can sketch that thing, you can sketch x of omega like this. X of omega is a summation of all impulses. Let me highlight them a little bit more in red. Impulse, 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 and so on. Keeps going, left and right. Those impulses are present at plus and minus k omega naught. So that means that those are integer multiples of omega naught right here. The scale, the weight of those impulses is 2 pi divided by t. So that's 2 pi divided by t in the Fourier transform plot. Now, what do you observe with this? Why are we calling this a special case? Well, the time domain signal is a periodic impulse train, and the Fourier transform of that is also an impulse train. So the impulse train is the only signal where the Fourier transform of a periodic signal is another periodic signal. It's a periodic pulse train, impulse train. The Fourier transform of that is another periodic impulse train. Next, let us take a look at some symmetry properties. Can we have some symmetry in frequency domain information when the time domain signal is even, maybe odd, maybe real? Can we say something about the symmetry in the frequency domain? And there are a bunch of properties over here that I have listed, which are also present in your reference tables. I'm going to prove one of them. And the type of proof that I do, you can apply that same strategy to prove other properties that are listed over here. So for example, I'll just say out a few properties here. If the time domain signal is even, then the Fourier transform of that even signal is also even. If the time domain signal is odd, the Fourier transform of it is also odd. If x of t is real, if the time domain signal is real, then you have a bunch of things that you can comment about. First thing is the Fourier transform has conjugate symmetry, which means x of omega equals x conjugate of minus omega. If x of t is real, it does not mean that the Fourier transform is real. It means that the Fourier transform of that signal is going to have conjugate symmetry. Now, this statement 3 can be broken up into two pieces, 3a and 3b. 3a is real part of the Fourier transform is even, imaginary part of the Fourier transform is odd. In the polar notation, you can say the magnitude of the Fourier transform is even and phase of the Fourier transform is odd. And similarly, you have a bunch of other properties as well. In the last property, I'm just highlighting that EV stands for that even part of the function. So Fourier transform of the even part of x of t is the real part of the Fourier transform x of omega. Now let us try to prove one of the properties, which is property 3. If we start off with x of t is real, that's what we have for property 3a, right? Like right here, 3a is this. That's what we are trying to prove here. X of t is real, then the property says it is going to have conjugate symmetry. And we are trying to see that if it does have conjugate symmetry, does it mean that the real part of the Fourier transform is even and the imaginary part of the Fourier transform is odd or not? We are trying to prove that. So let's go back to this and take a look. We know that if x of t is real, in time if it is real, then x of t should be the same as x complex conjugate of t. X of t, the Fourier transform of x of t, we are writing that as cap x of omega. Cap x of omega, because we are interested in isolating the real and imaginary parts, we are writing the Fourier transform of x of t as real part, which is real part of x of omega, which is r of omega, and imaginary part of x of omega, which is I of omega. Well, let me write that over here as well. R of omega is real part of x of omega, and I is essentially the imaginary part of x of omega. So far it's the general case, right? We are just saying, let us define x of omega to have this real part and that imaginary part. Then the property says x of t is real. So the time domain signal x is the same as x conjugate. This is time, right, of t. That particular so if x is same as x complex conjugate, then that implies that we are going to have conjugate symmetry in the frequency domain. X of omega equals x conjugate, complex conjugate of minus omega. That's property 3. Now using that, let us write the next statement. What is going to be x complex conjugate of omega? Well, we just need to find the complex conjugate of x. Okay, what is the complex conjugate of x? So x is right here. The complex conjugate of that is going to be that. Next, this property says x of omega is the same as x complex conjugate of minus omega. Well, if you substituted, if you did a minus omega substitution instead of omega, you can say this is going to go to minus omega here, this is going to go to plus omega there. Because we already have x of x complex conjugate of plus omega, then we can try to equate that to x of minus omega. So this goes here. What is x of minus omega? Well, take this guy right here and substitute minus omega there, minus omega there, minus omega there. So you get r of minus omega plus j of I of minus omega. Now, because we are able to use property 3 of conjugate symmetry, we can equate the real and imaginary parts. If you equate the real part, what do you get? R of omega equals R of minus omega, which implies the real part of the Fourier transform of x is even. That's property 3a. If you compare the imaginary parts over here, let's draw an arrow in blue. Oh, no. What do you have? Imagine negative I of omega equals I of minus omega. That means the imaginary part of the Fourier transform of x is odd. So both those statements combined, we have proved 3a. Let us next look at time and frequency scaling. And this is also a very intuitive sort of property, because if you make things slower in time, they become more and more focused in the lower frequency regions. If you make the time domain signal faster, if the changes in the time domain are faster, happening more rapidly, then you are essentially making them appear at higher frequencies, right? So this property just bridges that. So it just provides the details about those two statements. So the time and frequency scaling property says, if you have a time domain signal x of t, whose Fourier transform, so given, oh, we have already written that. The Fourier transform of x of t is x of omega. That is given. This is by using the definition of Fourier transform, integration from negative infinity to infinity, x of t e to the minus j omega t dt. You integrate out t, you are left with omega, you get the Fourier transform. If that is given, then if you scale the time domain signal by a scalar a, then in the frequency domain, you will have omega divided by a, the reverse, the reciprocal effect. But also there is a amplitude scaling of 1 divided by absolute of a. So the property essentially says that, but let's prove it. So the Fourier transform of x of at, right? We are after this. So the Fourier transform of x of at, where a is a scalar, is going to be x of at, substitute over there, and the rest of it is simply the definition of Fourier transform. Integral negative infinity to infinity, x of at e to the minus j omega t. Let's do a change of variable here. At, let's define at as tau. If you have at as tau, when t is negative infinity, the lower limit of that integration, tau is also negative infinity. So the lower limit of that integration doesn't change, as does the upper limit. Upper limit of that integration is plus infinity. With respect to tau, it will also be plus infinity. And we are assuming right now that a is greater than 0. So we are not looking at the time flipping, just we are looking at the time scaling. Now, since we do not want a to change sign on the limit of the integration, so let's see, if you do a d tau, what is d tau going to be? Dt is going to equal d tau divided by a. So we have d of tau divided by absolute of a, because we don't want to change the sign of that limits. Applying the new limits, and that, what do you have? Fourier transform of x of t equals 1 divided by absolute of a, right there. X of tau, where is that coming from? Because we simply substituted x of t with x of at with x of tau. But in the exponent, what do you have? E to the minus j omega tau divided by a. Where did we get that from? We got that by applying this. You see, we said if we have that e to the minus j omega t, for t we for at we substituted tau. So t will now become tau over a. The rest of it remains as is. Go back, take a look. E to the minus j omega tau divided by a. So everything else is the same. Now, if you look at this and compare it to the definition of Fourier transform, 1 over absolute of a remains as is. This is essentially the Fourier transform of omega divided by a, because this omega prime, the new omega, is omega divided by a. So that goes over there. So that's essentially your time and frequency scaling. Excuse me. You can summarize this property as this. You can say a fast changing signal. So things in time are changing fast, which means higher frequencies, right? So a fast changing signal in time means the signal contains high frequencies, and consequently is represented by wide frequency band, right? And then slow changing essentially means more low frequency components. So when you sketch out the Fourier transform, let me draw simply an x and a y axis, and just label this omega and label this x of omega. All of these regions correspond to low frequencies, closer to DC, closer to 0 frequency. Those are low frequencies. And as you go away from it, you are going higher and higher in terms of frequencies, right? 1 kilohertz, 2 kilohertz, 3 kilohertz, you are moving up in frequency domain. So if you are moving up higher in the frequency domain, that essentially means things are happening faster in the time domain. So if things get expanded in frequency domain, then things are getting compressed in the time domain. So changes are happening faster. And vice versa, right? So if things are getting slower in time domain, things are getting compressed in the frequency domain. All right, so that's your time and frequency scaling property. Now the next property is very interesting, and it becomes very interesting because you can go to several different Fourier transform pairs with this. And there are some math tricks that allow the concept of duality to exist in Fourier transform. So we'll look at this by starting off with two signals. Two signals are considered to be dual of each other in the sense of Fourier transform and the inverse Fourier transform, if the following is true. There are two signals, small x, capital X. Small x is a function, capital X is a function. For example, rectangle, sink, triangle, sawtooth, sine wave, anything, right? These are functions. Small x we typically use for time domain, and capital X is the function we use generally for the frequency domain. But if that is true, if the Fourier transform of small x is capital X of omega, then duality principle says if you just reversed the functions themselves, capital X here and small x there, with the same variable t and omega, then capital X of t, the earlier function in time domain, will have the Fourier transform of 2 pi multiplied by the earlier function x. Let me code this as a function of minus omega. So we are essentially interchanging the role of the functions small x and capital X. So this we know right away, right? X of t, the Fourier transform of that is x of omega. And if you want to go back, you just take the inverse Fourier transform to go here to here, right? So that is sort of what we have been doing so far, the one that is highlighted in pink. If you want to go from left to right, you take the Fourier transform. If you want to go from right to left, you take the inverse Fourier transform. For example, can somebody give me a Fourier transform pair in terms of functions? Anyone? All right, let's see. If I make this a rectangle, what do I have in the frequency domain? All right, thank you. Right, so if the function itself is rectangle, and if you want to go to sink, so you use the Fourier transform there. It's well, sine, but sink is also related to sine function, right? Sink x is sine x over x. So you can say sink, or you can also say sine. Both are going to be correct. But if you want to write it only in terms of one function, then sink. If you want to write it in terms of sine, you would say sine x by x, right? But coming back to duality, if you switch that function sync in the time domain, right, cap x, the function is in time, then the Fourier transform of that will be a vertically flipped rectangle with a scaling of 2 pi. That's the principle of duality. So the functions remain the same, but their role has interchanged. And so mathematically it works only because in the exponent, what do you have? In the definition of Fourier transform and in the definition of inverse Fourier transform, we have a similarity. The similarity is you have e to the minus j omega t and e to the plus j omega t. So that omega t product in the integrals in the definition of Fourier transform and the inverse Fourier transform allow this duality to work. On the left side, you have the time domain entities, x of t, which can be expressed as the inverse Fourier transform of cap x of omega as 1 divided by 2 pi integration over all omega cap x of omega e to the j omega t. The Fourier transform pair of that is x of omega, using the definition of Fourier transform now, is going to equal negative infinity to infinity x of t e to the minus j omega t dt. And if you see the similarity over here, e to the j omega t, e to the plus j omega t, right? So if you change the roles of the functions, if you change the variables t and omega, nothing really changes, right? We can go from one to the other. So mathematically, these are just two arbitrary variables, t and omega. We are attaching time and frequency attributes to them. But mathematically, they are just two variables, t and omega. You can interchange them. So we are going to use the duality in the following way. If you are given one transform pair, we can derive the dual pair. Like we did, rectangle to sync and then sync to rectangle. We can derive the dual pair where the time domain and the frequency domain functions are simply interchanged. We will first prove duality, then we will take an example at duality. Let's try to derive the duality equations first. If the Fourier transform of x of t is cap x of omega, then the duality principle says that cap x of t, the Fourier transform of that is going to be 2 pi small x of minus omega. So you're also flipping the signal. So whatever you have here, x of t, you change t to omega, but you also flip it about the vertical axis. And there is also a scaling, 2 pi. Okay, let's go back to the proof. Starting with x of t, what is this? This is definition of inverse Fourier transform. X of t can be written as 1 divided by 2 pi integration over all omega cap x of omega e to the plus j omega t d omega. Now substitute minus t for t, both in the left hand side and the right hand side. Bring out the factor 2 pi into the numerator on the left side. So you have 2 pi times x of minus t equals integration over all omega x of omega e to the minus j omega t. So you have essentially changed this over here and this over there. Next, interchange t and omega. We can do that, right? Mathematically, nothing changes. I'm just going from one arbitrary variable to another arbitrary variable. So what do you have? 2 pi x of minus t becomes x of minus omega Integration remains as is. Cap x of omega becomes cap x of t because we interchange the variable omega and t. E to the minus j omega t remains as is because even if you change t and omega, the product remains the same. E to the minus j omega t. D omega becomes dt. Now what is that? All of this, oh, come on. That is simply the Fourier transform of cap x of t. So we have changed the function small x to capital X. So the Fourier transform of capital X now is going to be 2 pi small x of minus omega, which is written up right here. So that's the proof of duality by simply changing the variables around. Now, let us actually use the duality property to find the Fourier transform of cap x of t, which is 2t1 sinc t1. What we know is the Fourier transform of a rectangle is sinc. So we start off with the Fourier transform of x of t, which is, let's see, Fourier transform is right here. Cap x of omega is 2t1 sinc omega t1. And you know, this t1, let me highlight that in blue. T1, you have t1 there, you have t1 there. You can also write x of t in bracket notation as it is 1 between minus t1 and t1. It is 0 otherwise. The Fourier transform of that is cap x of omega, which is 2t1 sinc omega t1. Now, using the duality property, let us try to find out the Fourier transform of t1 sinc t1. So we are leaving everything as is. We are essentially just trying to change omega to t, right? So that's how we go from here to here. Cap x of t is 2t1 sinc t1 now, right? That's essentially how you are using the duality now. Everything else is as is. So from duality, the Fourier transform of x of t is x of omega, which means that the Fourier transform of cap x of t is 2 pi x of minus omega. X of t is an even function. A rectangle is symmetric about the vertical axis here, which means the Fourier transform of cap x of t, which equals based on duality as 2 pi small x of minus omega, I can write as 2 pi small x of omega. I am able to write this step because this is even. What is 2 pi small x of omega? Well, first we do make this 2 pi and change the variable to omega. Okay, so if you multiply by 2 pi, this becomes 2 pi and this becomes omega. Everything else will remain as is. Maybe I move this a little bit out. Using those changes, we have written 2 pi of x of omega as 2 pi when omega is between minus t1 and t1, 0 otherwise. Sketch it out. the Fourier transform of a sink cap x of t, t1 sink t1 sink t t1. This is a sink in, this is a scaled sink in the time domain. The Fourier transform of that, using duality, we have derived that to be a rectangle with a height of 2 pi and a width of 2t1. Now, you know, there's usually a confusion about what is the difference between that and this, right? So if you see this double arrow, what does that mean? That means that if you want to go from time to frequency, you go from left to right. And if you wanted to find the inverse Fourier transform, then you go from right to left. So you could say that the inverse Fourier transform of 2t1 sink omega t1 is a rectangle with a height of 1 between negative t1 and t1. However, this one is saying something different. This one is saying this duality, after we apply duality, it is saying that if we had a sink in the time domain, then its Fourier transform is going to be a rectangle with a height of 2 pi between negative t1 and t1. And the inverse Fourier transform of a rectangle with a height of 2 pi between negative t1 and t1, the inverse Fourier transform of that will be 2t1 sink t1. Right? So going left to right for each of these is forward is Fourier, the backward is inverse Fourier transform. But the duality is completely switching the functions themselves. All right, let's let's do a few more steps to write this result in a very nice manner. What we had earlier is the Fourier transform of x of t, which is 2t1 sink t1. The Fourier transform of that, we wrote that as a rectangle with height 2 pi between negative t1 and t1. Now, I want this result to be in a very nice format. So I'm going to do some manipulation of this result. Essentially, I want this height to be 1, and I want this width. I don't want to call it T1. I want to call it, say, capital W. So I'm going to make those adjustments here. How can I make those adjustments? First, I divide throughout by constant 2 pi. So I divide, because linearity applies in Fourier transform. So I divide it here and I divide it here. Next, I'm going to change the limits from plus and minus T1 to plus and minus W, because T1 is a variable, W is also a variable. So if I change that from here to here, then I also need to change T1 here and here to W here and here. Of course, the factor 2 cancels out, right? This guy will cancel out. What you are left with is a result in a very nice format. The Fourier transform of W divided by pi sink WT is a rectangle with a height of 1 between negative W and plus W. The axis is omega. So we can write this particular Fourier transform pair, which is also present in table 4.1 in the primary textbook. Also appears in your Fourier transform properties tables that I uploaded on Piazza. W divided by pi sink WT, the Fourier transform of that is 1 between frequencies plus and minus W, 0 otherwise. So we will use this later on. We will use this later. All right. Now let's do something a little bit different. Before we go into time multiplication property, let us try to do something different here. Let us try to have two columns. Let's say we have time here and frequency here. And I'll just put a column in the middle, and let's say I have this. So I will write a function in time, just a function without all the details, all the aspects of the function. I'm just going to name the function, and I'm going to ask you guys to say something about the function in the frequency domain. So you have time domain on the left side, you have the frequency domain on the right side. If you had a rectangle in the time domain, what would you have in the frequency domain? All right, Ryan says sync. Absolutely right. Now, what if you had a sync in the time domain? What would you have in the frequency domain? Rectangle is right. Now let's play a game. What if you had a sync squared in the time domain? Let's actually do this. Let's do sync squared in the frequency domain. What if you had a sync squared in the frequency domain? Yes, wonderful. Triangle is right. And this is right because sync squared is multiplication of two syncs, which means in the time domain it's going to be a convolution of two rectangles. And because it is sync squared, that is telling me that they are the same sync function. So when you convolve two rectangles exactly the same, what do you get? You get a triangle. Absolutely right. And it actually works the other way as well. If you had a sync squared function in the time domain, because of duality, I hope you can say that it is going to be a triangle in the frequency domain. Right? This is based on duality, you can say that. In other words, you can say the multiplication in time domain will be a convolution in the frequency domain. Actually, let us kind of divide this up a little bit. Perhaps I can go down here and go down here. All right, let us do something different. Maybe I can do sync times sync. All right, let's do that. What if I had a sync function multiplied by a sync function, a different sync function? What would I get in the frequency domain? What shape? What trapezoid is absolutely right. And vice versa, right? Like if you had a trapezoid here, you would have a sync times sync here. Product. And the reason why you would have a trapezoid is because you are trying to now convolve two rectangles that are different. So when you convolve two rectangles that are different, you get a trapezoid. So in terms of their width, they are different. In terms of their height, if they are different, then you still get a triangle. But if then in terms of their width, if they are different, you get a trapezoid. Okay, so I hope you find this discussion helpful. It definitely helps me, because when I'm trying to work through Fourier transforms, this gives me a quick check, right? This gives me a sort of a quick check whether I'm doing in the right direction or not. Absolutely, yes, that's the goal, right? You use this property to make problems easy. You use any property, all the properties that you have access to make problems easier. And actually, because if you think about this, there are too many properties, right? There is multiplication in time, there's multiplication in frequency, there is duality, there is frequency shift, there is time shift. There are too many properties. So the best way to do the problems will be the application of the most appropriate properties. So for that, you have to kind of work through the math a little bit in your head, right? Which is something, something like this. Right now we are, trying to predict the shape of the functions. Something like this can help you predict how difficult or easy the math could be when you go down one particular procedure, right? One particular set of properties that you use. So absolutely, so this particular table doesn't have too many details because it's talking about functions, but you will have access to Fourier transform properties and Fourier transform pairs tables. Those tables you should use to your advantage as much as possible, right? So the question should, in my opinion, the question is slightly different, right? The question is not whether you can use the property or not. Yes, you can. That's given. Which property is actually the bigger question, right? Which property where is actually what makes the difference at the end. All right, let's move on here. We are trying to take a look at time domain multiplication. When we did the time domain convolution earlier, we saw that it was a convolution in time domain was resulting in multiplication in the frequency domain. Now, what if we multiply in the time domain? Using duality, you can quickly say, yeah, it is going to be a convolution in the frequency domain. Let us actually quickly prove that out. The proof over here is very similar to the proof for time domain convolution property that we did in the last lecture. So I'm going to quickly run through this. You have a multiplication in the time domain here, x1 of t and x2 of t. Let us assume that you are given this. You are given that x1 of t, the Fourier transform of that is cap x1 of omega. And you're also given that the Fourier transform of x2 of t is cap x2 of omega. Then the multiplication property, the time domain multiplication property, says that if you multiply these two signals in time, then you have a factor 1 divided by 2 pi, which wasn't there, by the way, in the time domain convolution property. And then you convolve the x1 and x2, their individual Fourier transforms. That particular convolution, what is that? That's a continuous convolution. But you're now convolving signals that are in the frequency domain. Same principles of convolution, a difference in independent variable. We are so used to doing the convolution in time domain, the independent variable is t, small t. Now we are doing that continuous convolution in the frequency domain. So the independent variable is now omega. That's the only difference. The principles of convolution remain the same. Now, this property is much easier to prove if we start off in the frequency domain. So let us define capital W of omega, the entire right hand side, as the convolution of x1 and x2, cap x1 and cap x2, and you're also including the 1 divided by 2 pi factor here. So what is small w of t? That is essentially the inverse Fourier transform of capital W, which can be written using the definition of inverse Fourier transform as 1 divided by 2 pi integration over all omega capital W of omega e to the plus j omega t d omega. That's definition of inverse Fourier transform. Capital W of omega, because it's a convolution, I can write that as 1 divided by 2 pi from over here. That is essentially right there. Just substituting for capital W of omega. Then we refer the continuous time convolution, or I shouldn't say continuous time, I should say continuous convolution integral. What is that going to be? I'm just going to write that over here, perhaps in red. Let me just write down over here. If I have x1 of omega and x2 of omega, x1 of omega and x2 of omega, and if I want to convolve those two, what do? Well, I will have an integral from negative infinity to infinity. What did I have earlier? I had x of tau, h of t minus tau. Now I'm going to have x1 of, instead of tau, I'm going to use theta. And then the other signal, h of t minus tau. Over here, now it's going to be x2, t minus tau. Now it's going to be omega minus tau, d tau, d theta. So all of that is, along with the 1 over 2 pi factor, is written over here. And then the other pieces are as is, right? This piece here and this piece here is the same. Next, we change the order of the integration, similar to what the time domain convolution property proof. Change the order of the integration. So now the integral becomes, first you do the integration with respect to omega, then you do it with respect to theta. You have 1 over 2 pi x cap x1 of theta. You pull that out because now that doesn't depend on omega. 1 divided by 2 pi integration over all omega cap x2 of omega minus theta e to the plus j omega t d omega. So I rearranged it. Then you observe what this is. That is essentially the inverse Fourier transform of x2, small x2 of t, but there is also a omega minus theta. So there is a frequency shift as well of theta. So I should also multiply that with e to the j theta t. So using the frequency shift property of the entire integral, we can write this 1 divided by 2 pi, the one that is highlighted here, right, as x2 of t e to the j theta t. Which is what we wrote over here. Next, the integration simplifies a little bit. We got rid of one integral. We come down to the second one. we notice that this term is independent of theta, so that can be pulled out of the integral. The remaining terms can stay inside. Once you recognize this, what do you have? This essentially, if you substitute, if you let theta to be equal to omega, another change of variable, what do you get? You see that this becomes, let's see, I'm going to highlight this in blue and then say this becomes 1 divided by 2 pi. You have integration, you have capital X1 of omega e j omega t d omega, right? Just do a theta equals omega, done. And you will see that that is essentially the inverse Fourier transform of small x of t. Or x1. So combining all those results, you can see that w of t is simply the product of x2 and x1 of t, which is essentially the time domain multiplication property. If you multiply things in time, you are essentially convolving here in the frequency domain, and vice versa, right? If you convolve in time, you multiply in frequency. In one property, in the time convolution, in the time domain convolution property, there is this 1 divided by 2 pi factor missing, but it is there in the time domain multiplication property. So just be aware of that additional factor, which is often missed. Okay. Now let us try to use the properties that we have learned so far and find the Fourier transform of x of t. Before we do anything, can you guys tell me the shape of the result? Before we do anything, I want you guys to picture the result now. You have sinc pi t divided by 2 multiplied by sinc 3 pi divided by 2. So different sinks being multiplied. So in the frequency domain, it should be different rectangles being convolved. So when you convolve, so here, multiply different sinks. Fourier transform, you have multiply the Fourier transform equivalent of multiplication, right? Fourier transform pair of multiplication is what? Convolution. Convolution, different rectangles. What is that? Trapezoid. You guys are absolutely right. So before we did anything, we already know the shape of the answer. It should be a trapezoid. If you don't get a trapezoid, you have gone wrong somewhere. That's the first thing that I like to do before I do any sort of these problems. Picture things in your head. All right, now what property, what reference result can I use? I have a sink, I have another sink. So I need the Fourier transform of a sink. All right, so let us try to look at the Fourier transform of a sink. What do I have here? All right, I have a Fourier transform of a sink right there, right? So I'm going to use this result. Let us sketch that result up quickly over here. So I will do that at the very bottom in red. So I will say in the time domain, I had W divided by pi sinc WT. The Fourier transform of that came out to be a 1. Oh, come on. The x-axis is omega. The y-axis is the Fourier transform of the signal on the left, and we have a rectangle between what is that, plus and minus w, minus w here and plus w here, and the height is 1. So that's a Fourier transform pair that I'm going to use to do all these problems here. So let me box that up as well. Reference result. So using this, the first thing I notice is this. If this is w, that needs to be w, so that I can have a w here, right? They all need to be w. All right. So the sink over here, the first sink is pi over 2 t. So that means this is pi over 2t. This means I need to manipulate the numerator to be pi over 2t, which will allow me to write its Fourier transform using the reference result as 1 between plus and minus pi over 2. So I'm introducing a new signal x1 of t as this. The next signal is x2 of t, which I'm using the second sink for. It is 3 pi divided by 2 there. It is 3 pi divided by 2 there, which means I need to have this in the numerator as well, so that I can write its Fourier transform with those as the limits. So I've essentially introduced two new signals here, x1 and x2. Can I say that x1 is x of t equal to x1 of t and x2 of t? Is it equal? Try to do this. You have sinks will be fine, right? Sink will match up. Sink functions will match up. But in terms of this, the amplitude of those sinks, you need 3 pi divided by 2, but you have half from here and 3 over 2 from here, right? So that means you have right now 3 over 4. So this is absolutely not equal, because you need to make, right now if you just multiply, it will be 3 over 4. You need 3 pi divided by 2. So essentially you need to multiply by 2 pi, right? So you still need to multiply by 2 pi. That will come later. But I hope you, the W will not match. Absolutely right. The amplitude scaling is not matching. But I hope you realize, I hope you see why you chose this particular x1, this particular x2, right? The main factor was this, right? The pi over 2t and 3 pi over 2t. The next factor was we had to use this particular reference result. So those two things made us define x1 and x2 this way. Next, we have to look at multiplying these two signals. When you multiply these two signals, we had half from x1, we had 3 over 2 from x2. We looked at that before, which gave us 3 over 4 earlier. But in the frequency domain, when you are multiplying in the time domain, you are doing a 1 over 2 pi and then convolution in the frequency domain. So when you do a convolution in the frequency domain, what do? Well, you can start off with what is going to be the lower limit of that convolution. It will be the sum of the lower limits of the signals being convolved. So try to do addition of these two. So when you do the addition over here, let's see, add it, what do you get? Negative 3 pi over 2, negative 3 pi, negative pi over 2. So you got, when you add those two up, you get negative 2 pi. Okay, when you add up the upper limits of the integration of the convolution, what do you get? You also get 2 pi, right? So by adding those up, the limits up, I already know that the integration starts at negative 2 pi and stops at, the convolution starts at negative 2 pi and ends at 2 pi. Now the only question that remains is, for how long will it increase and for how long will it decrease? For that, I need to find the difference between the widths. The width over here is 3 pi. The width over here is pi. So the difference between those two is 2 pi, right? And then if you split it up into two pieces, one is going to be pi here, the other is going to be pi there. So it will increase for pi and decrease for pi as it moves one inside the other, which tells me that this piece over here is going to be negative pi and pi. So by just using those shortcuts of convolving rectangles, I can come up with those 4 points. Now, the only thing that is left is for me to find the height of the trapezoid. What is the height of the trapezoid? Let us focus on the convolution height and then we'll scale it by 1 over 2 pi. When you do the convolution height, you have this shorter rectangle completely inside the wider rectangle, and you are integrating over all that omega. So height of this 1, height of this 1. The width of the narrower rectangle pi. So 1 times 1 times pi is going to be the height of the trapezoid. That's the contribution from the convolution. So you get pi there. And then 1 over 2 pi because of the time domain multiplication property. Multiply them half. That's the height of the trapezoid. That's it. The last step is to make the 3 over 4 become 3 pi over 2. So from 3 over 4, how can I go to 3 pi over 2? I just multiply everything by 2 pi. If I want to multiply everything by 2 pi, the height of this, right, was half earlier. From here it was half. I need to multiply 2 pi here. So all I'm changing is multiply 2 pi there because I multiply 2 pi there. So the Fourier transform of the desired x of t is going to be a trapezoid with a height of pi, and it'll increase between negative 2 pi and negative pi, and it'll decrease between pi and 2 pi. All right, so let me take a look at the chat box for couldn't we use linearity and multiply by 2? Couldn't we use linearity and multiply by 2? Couldn't we use linearity and multiply by 2? I'm not for x1 multiplied by x2. Well, for x1 multiplied by x2, so x1 and x2 are time domain signals and they are getting multiplied, right? How would I use linearity? Because linearity only applies when you are multiplying time domain signals with scalars. Over here we are multiplying two time domain signals. So I would have to use a time domain multiplication property. Right, it only works for scalar multiplications. All right, like there's another question. How did you get half at the first transform? Right here. So the question is about this, right? Okay, so how did I get the height to be half? So they are in two pieces, right? The first piece is when I multiply the signals in the time domain, then the Fourier transform of that is going to be a convolution in the frequency domain, but there is also a factor 1 over 2 pi addition, right? There's additionally 1 over 2 pi factor there. Okay, so that's where the 1 over 2 pi came from. Now I need to look at the convolution between those two rectangles and the maximum convolution result, right? Because I'm going for the height of the trapezoid. So that's going to happen when the wider rectangle is completely inside, the narrower rectangle is completely inside the wider rectangle. That's when you get the height, the height of the trapezoid. And we know that this guy is pi and this guy is I believe 3 pi. So what is going to be like integral x1 x2 integral over all the omega d omega? What is that going to be? Well, if this is 1 and this is 1, it is going to be integration between 1 and 1 and overlapping frequencies. What are the overlapping frequencies? They only happen for pi, right? So whatever that is, minus pi over 2 to pi over 2, or you can do 0 to pi, whatever that is. The width of that rectangle, overlapping rectangle, is going to be pi. So it will be from the convolution, it will come out to be pi. So it will be 1 divided by 2 pi from the property, pi from the convolution, you get half. You see it? All right, I'm going to let this, perhaps I can just erase this. I can let the others be as is, right? Yeah. And then the last step is straightforward. So I think you guys get that. All right. The frequency shift property. We are revisiting the frequency shift property. And this time we are actually using the time domain multiplication property to look at this. So when if I consider two signals being multiplied, one of them is x and the other signal is e to the j omega t, I can use a time domain multiplication property to look at this. The frequency shift property claims that if you multiply the time domain signal by e to the j omega t, it is reflected in the frequency domain as the Fourier transform of x being shifted by omega naught. We have seen this earlier. We have actually proved this earlier as well. This time we are proving it in a slightly different manner, which is product of these two signals x1 and x2 is 1 divided by 2 pi x1 cap x1 convolved with cap x2. What is that? That is our time domain multiplication property. And we are letting x1 be x of t, color code yellow. We are letting x2 be e to the j omega naught t, color code blue. The Fourier transform of those two signals, for x, it is cap x of omega. For x2, we need the Fourier transform of e to the j omega naught t. What is it? Well, for 1, the Fourier transform is 2 pi delta of omega. So for e to the j omega naught t, the Fourier transform is going to be 2 pi delta of omega minus omega naught. So the Fourier transform of e to the j omega naught t is 2 pi delta of omega minus omega naught. Now let's go back. Multiply in time, convolve in frequency. So when you multiply x of t e to the j omega naught t, that's in time domain. In the frequency domain, it's going to be a convolution of x1 and x2 and also a factor of 1 divided by 2 pi. 1 divided by 2 pi remains as is. For x1 of omega, you have x of omega, the Fourier transform of small x of t. That comes over. And then convolved with, you have the Fourier transform of e to the j omega naught t, which is 2 pi delta of omega minus omega naught, an impulse at omega naught. When you convolve any function with an impulse present at some other location, the function will shift to that particular location. We know that using the properties, convolution with an impulse properties. So you have 1 over 2 pi and this. So first of all, this gets cancelled out, right? Like this guy gets cancelled out with 2 pi. You will be left with x of omega convolved with delta of omega minus omega naught, which is simply x of omega minus omega naught. Any signal x of omega convolved with a shifted delta function results in that signal being shifted x of omega minus omega naught. So where is this coming from? This is essentially coming from, let me write this over here, convolution with an impulse. Right, so that's essentially what's going on. So we are revisiting this frequency shifting property. Why? Why are we revisiting this frequency shifting property? And it happens to be soon before we start talking about communication systems. So why do you think we are talking about this right now? Soon before we start talking about communication systems, we are talking about a frequency shifting property. Soon before that. And the reason is this. When we start talking about communication system, you will see that in order for me to transmit a message, a voice signal, or any sort of signal from point A to point B, I need a carrier. I need a different signal that allows me to go from point A to point B. So I have a signal, the message signal, and I also have a carrier signal. So think about a piece of paper, right? If you wanted to throw a piece of paper, what would you do? So suppose you wanted to throw the piece of paper really far away from you. What are your options? Some would say, I will crumple the piece of paper into a ball and throw it, right? Some probably will say, I will make it into a paper airplane and fly it. Paper airplane, sure, paper airplane and throw it, right? But the real question is, for the same piece of paper, if I roll it up into a heavy stone and I tie up the paper, and inside that I put a heavy stone which is acting like the carrier, I will be able to throw it really far away. So I will be able to, so there is a carrier and there is a signal. There is a carrier signal and there is a message signal. And when you put the message signal onto the carrier, you are essentially going to be doing this frequency shift operation, which is why we are revisiting this. And it has to do with moving the Fourier transform to a particular frequency omega naught. More about this later on. So that's where we are going with all of this discussion. So the first step, or the preliminary step, I should say, before we start talking about communication system, is to talk about the Fourier transform of the product of the two signals. The product of two signals, one of the signals is m of t, small m of t, small m corresponding to message. The other signal is a cosine omega naught t. So this is essentially, this is my message and this is my carrier. Now let us come back to the Fourier transform world. Let us just treat this as an example problem. You are given the Fourier transform of m of t, right? You are given that m of t has a Fourier transform of a triangle. By the way, what shape is small m of t? Cap m of omega is a triangle. Small m of t should be what shape? Yes, sinc squared is absolutely right. So, even though that is not a part of this problem, but I like to kind of, have this, continuous assessment. Okay, what is happening in the time and frequency domain? So that'll help you go in a smoother manner and probably an easier procedure. All right, so let's come back. The Fourier transform of m of t is given to us. It is a triangle in the frequency domain. The cosine omega naught t is the another function of time. We are trying to multiply them. We can show this multiplication process in a schematic, in a block diagram format like this. There are two signals being multiplied. One is the cosine signal, and I'm calling that the carrier signal. And then the other signal being multiplied in this mixer, or a multiplier. This is my multiplier here. Is m of t. I've called m of t my message signal, for which I know the Fourier transform. I know that the Fourier transform of this guy is m of omega. So I'm trying to find what? The Fourier transform of x of t. So I'm trying to find the Fourier transform of this guy, right? So I'm essentially after cap x of omega. So how do I do this? Well, one way of doing this is probably the time domain multiplication property. So if I want to use the time domain multiplication property, then I'm going to have to use, I'm going to need to know the Fourier transform of both the signals that are getting multiplied. So what is the Fourier transform of cosine omega naught t? Let us write this over here. So I have cosine omega naught t. The Fourier transform of that I know from earlier discussion to be pi delta of omega minus omega naught plus delta of omega plus omega naught. And I also know the Fourier transform of m of t. It's a triangle that's given to us. All right, so let's try to multiply them. On the time domain side, I have m of t multiplied by cosine omega naught t. And in the frequency domain side of things, what am I going to have? I'm going to have of course, I will start off with 1 over 2 pi because of the factor there. Then I need m of omega convolved with all of this. All right. Perhaps I need one more. Right, m of omega convolved with two impulses, one impulse at minus omega naught, the other one at plus omega naught. So how can I write this out? Pi gets cancelled probably, right? And then I have what? I have only on the right side, I have m of omega minus omega naught, half of that, plus half m of omega plus omega naught. All I did was I used my frequency shift property that I just looked at over here, right? When I convolve with an impulse, I move that signal to that frequency. Half coming from the amplitude scaling there. So, you know, in terms of frequency, we can look at all of this as that. Let's take a look at another one here. All right. So what we did was let's see. This was m of omega. When we convolve this with two impulses, right, this was W, oh, come on. This was W, this was minus W, and this was 1, and this was m of omega, and this was omega. When we convolve that with the Fourier transform of a cosine, omega naught t, the height was pi, this is 0, this is what, omega naught, this is minus omega naught, this is omega. So when we convolve this with those two impulses, what we end up with is the two rectangles, two triangles that will be now centered at omega naught and minus omega naught. And this point is going to be what? Omega naught plus W, omega naught minus W. What is this? Minus omega naught plus W, minus omega naught minus W. What is the height? Oh, come on. And we have this. What is the height going to be? Height is going to be half. Is it going to be half? Right, it is going to be half. This is going to be cap x of omega. This is omega. So you see what happened here. I think of this as m of omega, when I convolve that, when I multiply that with a cosine, half of the message moves up to plus omega naught, and half of the message moves down to negative omega naught, right? So this is moving up in frequency and moving down in frequency. But that move, right, how far up in frequency does it go? Well, that depends on the omega naught. The higher the omega naught, higher it will be on the x-axis over here. But one triangle splits up into two half triangles. One is at plus omega naught, the other is at minus omega naught. Simple as that, right? I should also point out that that convolved with that, but I also multiplied it with the factor here, which is 1 divided by 2 pi multiplied by all of that, right? Like so, x of omega is 1 divided by 2 pi multiplied by the convolution of those two things. All right. If you guys can bear with me for just a couple more minutes, we can finish this example off. So this is what you do at the transmitting end of things. You up convert a signal. You put the signal onto a carrier. You multiply it with a high frequency cosine signal. And what you transmit is going to probably look like this, x of omega. In frequency, it's the same triangle, but it is up converted, right? And in terms of the nomenclature, this is called a signal at baseband, centered around DC. And this is signal at passband. So we have up converted the signal in frequency, shifted it up and down. Now let us try to answer this question. What happens if you multiply m of t with cosine omega t, with a cosine omega t? So now what you have is m of t multiplied by cosine. We already know that. What happened to that? Now, if you multiply it again by a factor by cosine omega naught t, what do you think will happen? Well, when you multiplied this guy with the first time, it moved up and down. Half of it moved up, half of it moved down. Now, when you do the same thing again to this, what do you think will happen? This guy is going to move, right? This guy is going to move up and down in frequency, and this guy is also going to move up and down in frequency. Half of each piece will move up and down on both sides, which will result in something like this. I have my x-axis over here. I'm simply sketching in the frequency domain. For the triangle at plus omega naught, I'm going to have, right, you see this guy will move, this triangle will move plus omega naught and minus omega by plus omega naught and minus omega naught. It is already at omega naught, so when it gets multiplied with another cosine at omega naught, it will go to 2 omega naught, and then the lower portion will come down to DC, 0. So half of it needs to go up, and down. So that will now be at 2 omega naught. And you will also have a triangle, half of it over here. And from the left triangle, you will have one guy here, and you will have another guy here. They will get added up at DC, which means you will have that. half getting split up, you got 1/4 here, you got 1/4 here, and half getting added, you get half here. This will be at -2 omega naught. This will be at 0. This is at omega. This is the Fourier transform of m of t cosine squared omega naught t. Now, this is essentially what happens at the receiving side of things, right? You transmit a signal, which will have the Fourier transform that looks like this. When you receive it, you multiply the signal with the same cosine that you used at the transmitter, same carrier signal, and then you essentially use a low-pass filter. So if I put a low-pass filter here in frequency, I can just extract the signal out, right? So I can say that as if we use a low-pass filter, we can extract m of t, at least half of m of t, and reject 2 omega naught and -2 omega naught terms. And the low pass filter should be like the one in blue, right? So the one in blue, the only criteria is the cutoff frequency of that low pass filter has to be greater than W, right? So because this will be W with the higher frequency of the message, the cutoff of this has to be greater than that. All right, we will revisit these topics when we come back. And we'll start talking about communication systems when we come back. That's it for today. Let's see, where is my stop recording?